When we talk about gravitational field strength, G, what we're talking about is the force that's applied per kilogram of mass of an object. So G in newtons per kilogram. And it varies, as we've seen, with the radius, the distance from the planet. So G is really just the force per kilogram. So it can be found by G times big M divided by R squared. This is really just what you get if you make M equal to 1. So this is the gravitational force experienced by 1 kilogram is the gravitational field strength. So it's the force per kilogram. And we know that as these objects get further away from the thing that they're attracted to, the large body, here their gravitational force will weaken. And so the gravitational field strength as you move away from the surface will reduce. We know that on the surface of the Earth, the acceleration of a projectile in free fall, experiencing no other forces, will be negative 10 meters per second squared, because the gravitational field strength of the surface of Earth is 10 newtons per kilogram. And the interesting thing is, as you go up away from the Earth's surface, this follows as well. So wherever you are, so long as gravity is the only force acting on you, your acceleration will always equal g. And so acceleration of a satellite will also equal gm on r squared. So it's important to remember that your acceleration is the same as the gravitational field strength at any point in space. We discussed in another video about how if you graph gravitational force against orbital radius, you get a nonlinear graph. It's part of a sort of y equals x squared sort of graph. And one of the things that you're often asked to do with this graph is to calculate work done, or energy gained or energy lost, or even velocity gained or lost as objects move towards or away from gravitational attraction. And so the technique for doing this revolves around calculating the area under the graph. Now, take note of the scale on the vertical axis. It will either be in an axis of force, measured in newtons, or in gravitational field strength newtons per kilogram. You need to be very careful with that. If it is a force axis, then what you have here is a force extension graph, a force times distance graph. And so the area under this, as we know, will tell you the work done, so the amount of energy gained or lost. So if you're asked about two altitudes, A and B here, the work done by gravity on an object moving between these 2 points will be equal to the area under the graph between these 2 points, providing that the vertical axis is in newtons. If it's not, if it's in newtons per kilogram, as it is here, you'll need to multiply this area by the mass of the object. So this area will tell you either the kinetic energy gained or lost, the gravitational potential energy gained or lost, and then from kinetic energy you can even work out the velocity that's been gained or lost. And so we do this by counting the squares. This will often form a little grid. So we can count the squares, getting an approximate value for the squares up here. There's always a margin of error that assessors will accept when they're marking these questions. So we count up these squares, we calculate the area of one square, looking carefully at this vertical axis, making sure that both of these scales run to 0 all the way down here, and they're not truncated like this, which will mess with your calculations a little. You'll need to take that into account. And so this area under here tells you either the energy that's been gained by something falling towards the surface, or the work that's had to be done against gravity moving away from the surface.